Okay, this is lesson 2.1a and it's on equivalent polynomials. We'll start off discussing what a polynomial is. So I've included a definition and some characteristics that I'm going to go through now, and then we'll talk about some examples and some non-examples. So what is a polynomial? Well, it's an expression in which each term is the product of a constant and a variable that has a whole number exponent. And the key to the polynomials is that all of the exponents on the variables are going to be whole numbers, so numbers that aren't negative. The exponent can be 0, and that variable term cannot be there. But if there is an exponent that is a number like 1, 2, 3, 4, it has to be a positive number. So a couple examples. We got 2x plus 1. This is a two-term polynomial or a binomial. It's got a coefficient on an x, which is your variable. The exponent on this x would be 1, and then it's got a constant term, plus 1, which doesn't have a variable. Or you can think about it as if it does have a variable, like x, but the exponent on that variable would be 0, which is why it's not written. So you can see through this example that there are no negative exponents. Another example would be like a quadratic polynomial. So we're going to have it like a 2x squared plus 3x minus 4. And again, only positive exponents and variables with coefficients and then constant terms. It doesn't have to have a constant term, it can just have variable terms. Like it could be something like x cubed minus 3x squared. Or it could have like 4 or 5 terms, like maybe x to the exponent 7 minus 2x to the 5 plus 3x squared minus x plus 4. And again, that's another polynomial expression. Notice that these are fully simplified polynomial expressions. They only have unlike terms, so we can't simplify this any further by adding like terms. And again, what's a like term? Well, a like term is a term that has a variable with the exact same exponent. If you have like terms, you can simplify them by adding or subtracting. So if we look at the characteristics now, a polynomial will include any combination of constant terms, variable terms, and variable terms with whole number exponents. And the like terms would be simplified. Some non-examples. Well, we could have something with a negative exponent, like we could have x to the negative 2 plus 3x 4. Since there's a negative exponent, we don't have a polynomial. It could be like a rational expression, so like 1 over x plus 1. That's not a polynomial, even though there's not a negative exponent on that x. If we were to write this not as a rational, it would actually have a negative 1 exponent. But I guess the easier way to think about it is that if you have any division and there's an x in the denominator, it is not a polynomial. The absolute value, that's not a polynomial. So like the absolute value of x minus 3, that expression, not polynomial. That's an absolute value expression. Same with the square root. If we had like the square root of x plus 2, that's not a polynomial. Or if we had like a trig, like say we were doing like sine x, and we'll talk more about something like this later in the course. But all of these are not polynomial. The rest of this lesson is about equivalency. So what's it mean if a polynomial is equivalent? Well, it means a couple things. So I've got 3 polynomials here. And if I were to put these 3 polynomials into a graphing calculator, if I were to graph f of x, g of x, and h of x, I would get the exact same graph. And that's the first way to determine if something is polynomial. It's to graph it. 2 ways to determine if functions are polynomial. It's to graph. And if we graph these polynomials, we should get the same graph for all 3. And when I graphed it on Desmos, I actually did get the same graph for all 3. And if you get the same graph for all 3, the exact same graph, it means that they're equivalent. Why would we get the same graph from graphing these 3 things? They all look different. Well, the reason we end up getting the same graph is because these are 3 forms of a quadratic. And in fact, they're 3 forms of the same quadratic. So how can you tell that they're the same? Well, you could turn them all into one form. So let's review the forms of a quadratic. The first one, as it's written here, is actually in vertex form. I'll just write a V for vertex. This form here with the brackets is factored form. And the last form is standard form. And we're not going to do a ton with quadratics in this unit, but it's a nice point to start so we can talk from a point of reference that everyone can kind of remember. And if you don't, that's okay too. But vertex form tells you stuff about the graph, factored form tells you stuff about the graph, and standard form tells you stuff about the graph too. But since they're all in different forms, it's hard to tell that they're the same. So let's change them all into one form. And the easiest way to do that is just to expand. So if we expand our quadratic in vertex form, we would get something that looks like this. 2 times x plus 2 squared means write the x plus 2 bracket down twice. Remember, because we have to use BEDMAS when expanding, we deal with the exponent before multiplying. We're not going to multiply the 2 in before we write the bracket twice. Now we can multiply or distribute the 2. But instead, actually, I might simplify in the brackets first. So I'll leave the 2 out. And then I'll FOIL. X times x is x squared. X times 2 is 2x. 2 times x is 2x. And 2 times 2 is 4. And then I'm going to collect like terms in my bracket. So I'll get x squared plus 4x plus 4 minus 18. And now I can distribute the 2. 2 times x squared is 2x squared. 2 times 4x is 8x. 2 times 4 is 8. Minus 18 is outside. Collect like terms one more time. We get 2x squared plus 8x minus 10. And if we compare it to our standard form, it's the exact same. So our vertex form was hiding the fact that it's actually the exact same as the standard form. We could only tell by graphing, but now we can tell because we changed forms. So the second way to show that functions are equivalent is to simplify algebraically. And in this case, it meant expanding. If you end up with the same expression after simplifying, you have equivalent expressions or equivalent functions. We could have chose to turn them all into vertex form. It would have just been more work because we would have had to expand the factored form first and then complete the square. And then we would have had to complete the square. It's more work, so expanding is actually a quicker method to make them all look the same. Let's expand the factored form and make sure it's the same too. We kind of know it is because it gave the same graph, but let's do it anyways. We'll leave the 2 out, and I'm going to FOIL. X times x is x squared. X times 5 is 5x. Negative 1 times x is negative x. And negative 1 times 5 is negative 5. Collect the like terms in the brackets. 5x minus x is 4x. And now distribute the 2. 2 times x squared is 2x squared. 2 times 4 is 8x. 2 times negative 5 is negative 10. And indeed, we do end up with the exact same. So therefore, f of x is equal to g of x, which is equal to h of x. They are equivalent. Now let's consider one of those common algebraic errors that we looked at in the review unit. In one of the practice questions, there was common algebraic errors, and one of those errors was this. And it says that x minus 1 squared is not the same as x squared minus 1. And the reason why people think that this is true is because what they do is they just square the x and then they square negative 1, and they end up getting the same thing, which is wrong. And in fact, it would have been wrong because you should have got plus 1. But the reason it's wrong is because they aren't the same if you simplify them. So there's two sides, a left side and a right side. Let's look at the left side first. The left side says x minus 1 squared. The way we simplify that is by writing the bracket twice and expanding by FOIL. X times x is x squared. X times negative 1 is negative x. Negative 1 times x is negative x again. And negative 1 times negative 1 is positive 1. And if we collect our like terms, negative x and negative x makes negative 2x. This expression is not the same as the right side. The right side was x squared minus 1. They aren't the same. The left side does not equal the right side. Therefore, they're not equivalent. So when we look at ways to determine that things aren't equivalent, simplifying algebraically to show that the expressions are different is one way to show that they're not equivalent. So I'm going to keep that in the same spot as above. If you simplify algebraically by expanding, and you get different expressions, they aren't equivalent. In fact, if you, in Desmos, graphed the left side and the right side, if they were equal, you'd end up with the same graph, and we actually end up with these two graphs. The one on the left here is the x minus 1 squared, and the one down here is the x squared minus 1. And actually, if you think about transformations, you could have come up with that pretty quickly too, because this would be a shift to the right 1, and this would have been a shift down 1. That negative 1 is a D, that negative 1 represents C. Those are two different transformations. So of course they don't look the same. So the first way would have been to graph. If you get different graphs, they're not equivalent. Now why are there three ways? Well, because it's actually really easy to prove something's not equivalent. It's way harder to prove that things are equivalent, because to prove they're not the same, all you have to do is demonstrate it for one value of x. And once you've proved it for one value of x, you can say that it's not the same. Because as soon as it's not the same once, or not equivalent once, it's not equivalent. It's harder to prove that they are equivalent because you have to prove for every value of x that they're the same. So the third way is to check a value for the input. And if you get different outputs, it's not equivalent. And you can't use this strategy to prove equivalency, but you can use it to prove they're not equivalent. So here, let's do a check. Let's do a check, and we're going to test a value. So let's test x equal to 0 and see what we end up with. So on the left side, that would be 0 minus 1 squared. 0 minus 1 is minus 1, minus 1 squared is 1. On the right side, if we try negative 1, that would be 0 squared minus 1. 0 squared minus 1 is negative 1. They're not equivalent. So that means for that one value, they're not the same, which means that they're not the same for every value of x. And as soon as they're not the same once, they're not the same, and you can say they're not equivalent. All right. That's it for the first part of the lesson, 2.1a, equivalent polynomials. There is a second video to this lesson. So after you're done with this video, please go watch part B. Thanks for watching, and I'll see you next time.